This ECE 201 lesson is titled Kirchhoff Connection Constraints on Current and Voltage. Some of the equations used in analyzing circuits and solving for current and voltage come from how the various elements are connected together. These are referred to as connection constraints on I and V, connection constraints on current and voltage. And there are two, Kirchhoff's current law and Kirchhoff's voltage law, or KCL and KVL. Let's focus now on KCL, which is applied to nodes in a circuit. A node is an electrical juncture of two or more devices. Here we see two devices. This is an electrically controlled valve. Here's simply an on-off switch. Here the two wires have been just physically twisted together, and for good measure we can add a wire twist cap. And this would be an example of a node in a circuit, or it might be the juncture of two aluminum lines on an integrated circuit chip or two traces on a printed circuit board, but let's consider this as a concrete example for right now. Charge is conserved and charge does not accumulate at a node, so we could express that physical fact by saying that if we have a current I1 and a current I2, then I1 would have to be equal to I2. In other words, if there's 3.2 coulombs per second flowing into the node, and I1 is equal to 3.2 amps, then I2 is also equal to 3.2 amps. Now we have a third wire, so there's going to be a third current I3. Do we want to have the arrow in I3 pointing away from the node or toward the node? It doesn't really matter, but in either case we want to have a systematic algebraic way of writing Kirchhoff's current law at that node. KCL can be expressed as a regular English sentence as just saying, quote, the algebraic sum of currents entering a node is 0, unquote. Suppose we apply that to this particular node, part of a bigger circuit not shown, but we have four currents associated with this node. First, put down an equal sign, and on the right side of that equal sign, put down a 0, and then list all the currents. We have I1, I2, I3, I4 on the other side of the equal sign, and assign plus and minuses associated with these currents as follows. If the current arrow head is pointing into the node, such as I1, use a plus sign. If the current arrowhead is pointing away from the node as I2, then use a minus sign. So I'll have plus I1, I'll have minus I2, plus I3, and plus I4. Algebraic sum of the currents is equal to 0. Or sometimes people say, well, the sum of the currents entering a node is equal to the sum of the currents leaving the node. You can implement KCL from that perspective by putting down an equal sign, and then on the left-hand side, put down all the currents that have arrowheads pointing into the node, I1, I3, I4, and on the right-hand side, simply put down the currents, as many as there are, who have arrowheads pointing away from the node, in this case I2. Now these two equations are algebraically the same. You could add I2 to both sides of this first equation that we get, and we get the second equation. But adopt a method to systematically write down KCL at a node, and that would give you one important set of connection constraints, one important set of equations that we need to solve circuits. We've been showing the node as a single point, but on a circuit schematic, more generally, the node consists of all the zero resistance wire from the node to each element. For example, on this circuit, we would not say that there are 6 nodes. Instead, we could think that all of these points are one single connection point. You could think of them as all being drawn together, connected to one solder point or to one wire cap. And likewise, all of these could be under one wire cap if we want to have that particular physical picture in our mind. So really, there's just two nodes, the top and the bottom. Here's another perfectly good way to redraw that circuit. looks quite different perhaps than the first one, just as it meets the eye, but it's saying the same thing about the circuit. What elements are in the circuit and how are they connected? Either way it's drawn. Suppose we apply KCL to this. We could talk about currents I sub A, I sub B, and I sub C. At the top node, I'll put down my equal sign, 0 on the other side. My three currents, I sub A, I sub B, and I sub C. I sub A flows into the node, it has a plus sign. I sub B and IC flow out of the node, they have negative signs, so that would be my Kirchhoff's current law at the top node. The bottom node, what do we have? Put down my equal sign, you have a 0. I sub A is flowing out of that node. I sub B and I sub C are flowing in. And this is the equation that we would have from KCL at the bottom node. Well, we see quickly, don't we, that these are really the same thing algebraically. We just multiply the top equation through by -1, we get the bottom equation. They are not independent equations. And this brings up an important thing about Kirchhoff's current law. If you have capital N nodes, the number of independent KCL equations that one can write is capital N minus 1. Let's consider applying element constraints from our previous lesson in the Kirchhoff current law that we've talked about so far today to solving this circuit, that is to find all the unknown currents and voltages. There are 4 elements, 2 terminal elements, and so there are going to be 4 currents, 4 voltages. That means there's 8 unknowns. Let's identify these on the circuit. Here I've written the 4 voltages along with plus and minus reference signs. Once I put those down, put the current arrows in such a way that passive sign notation is followed. Now, the element constraints are what? For the 3 resistors, Ohm's law, V equals IR. For the voltage source, the ideal voltage source, it's V1 is equal to 6 volts. Let's write down those 4 element constraints. The 4 equations in the box are what the elements bring to the table before they're hooked to anything. The R2, 40 ohms says, however you connect me, V2 will be equal to 40 times I2. How about KCL? We can identify 3 nodes. Let's call this node A, this node B, and this node C. At node A, KCL may be expressed as minus I2 minus I1 is equal to 0, or equivalently I1 plus I2 is equal to 0. And at node B, we can write that I2 minus I3 minus I4 is equal to 0. Those are 2 independent KCL equations. We could also write down an equation at node C. It would be a good exercise to do so. You'll find that it results in an equation that is derivable from what the equations at A and B. So it's not an independent equation. And here are the 2 KCL equations written in box form. We have 4 plus 2 equations, 6 independent equations. We have 8 unknowns. Where do the other 2 equations come from? They will come from Kirchhoff's voltage law, and that's the next thing we wish to discuss. Kirchhoff's law expresses conservation of energy associated with the electric charge. Let's just consider as an analogy a force that we have more everyday experience with, gravitational force. As I lift this stone, I change its gravitational potential energy. If I start at a certain height and then I change the stone's height, when I return to the original height, it has the same potential energy that it started with. Potential energy is conserved in that trip through space. As charge moves through a circuit and experiences voltage rises and voltage drops, its potential energy also changes. But if we make a closed loop through the circuit, the potential energy when we return back to the starting point has to be the same as it was at the beginning of that traverse. And the implication is, just in terms of a plain English sentence, in terms of circuit variables, is that the algebraic sum of voltages around a closed loop is equal to 0. That's KVL, Kirchhoff's voltage law. Let's consider a clockwise loop starting at this point, going around this loop, coming back to the origin again. One way to implement KVL is put down an equal sign. On the right hand side put 0. On the other side put all the voltages that encountered in going around the loop. And if we enter the voltage at the minus sign, use a minus in front of the voltage. If we enter it at the plus side, use a plus in front of the voltage. The algebraic sum of voltages around that loop is equal to 0. Or alternative, sometimes people implement KVL by saying the sum of voltage rises is equal to the sum of voltage drops. In that case, again, put down our equal sign. On the left-hand side, let's add up the voltage rises, going from minus to plus, and on the other side, let's put the voltage drops, going from plus sign to minus sign, and these two equations are algebraically equivalent. There is a situation where KVL does not work, but we'll not be considering such circuits with time-varying magnetic fields coupling to the loops in 201. So now let's return to that circuit for which we have 8 unknowns, and we only had 6 equations, 4 from element constraints, 2 from KCL. Let's bring KVL into the picture. And let's consider 2 loops. Say this would be loop 1 and loop 2. For loop 1, we can say that minus V1 plus V2 plus V3 is equal to 0. And for loop 2, we can say that minus V3 plus V4 is equal to 0. Could we have also written the KVL around the outer loop, minus V1 plus V2 plus V4 is equal to 0? Certainly. And that would be just as valid as any of the others, but you can convince yourself that it will not bring any new information to the table. So not all KVL equations will be independent KVL equations. So going back to the schematic we've been drawing on paper, we've added 2 more equations from KVL, and we now have 8 equations to solve for 8 unknowns. Note that half the equations came from element constraints, i.e. what components we picked out of the components bin, and the other half come from connection constraints, how we connected them. These 8 equations can be solved by whatever linear algebra methods we like to use, but these are the numerical results. We'll leave that as an exercise. As we will proceed with ECE 2.1 lessons, we'll come to regard this method to be rather cumbersome, perhaps not very elegant. We might look at this circuit in the future and say, I believe I'll tackle that with mesh current analysis, or perhaps I'll use node voltage analysis. Or actually, for a circuit of this type, we should be able to solve it eventually in our head. We can use voltage division, current division, source transformations, or we can use combined resistors in parallel, combine them in series. But regardless of what methods we use as we go on, let's remember that all of them, whatever their name, go back to the foundation concepts of element constraints and connection constraints. KCL, KVL, and element constraints are the foundation of what we use in circuit analysis. We may summarize the situation then by noting that if we have a circuit with capital E elements, and there are 2 terminal elements, we're going to need 2 E equations, right? Now, E of them will come from the element constraints. N minus 1 come from KCL, and the remainder, which is E minus N plus 1, where E is the number of elements and N is the number of nodes, those remainder come from Kirchhoff's voltage law. Well, this ends the ECE 2.1 lesson, Kirchhoff connection constraints on current and voltage. We've discussed KCL, KVL, and seen how those can combine with element constraints to provide solutions to a particular circuit.